It's a real pleasure to be back here at the QCrypt conference, and I'm sure it's going to be a very interesting meeting this week. And it's also a pleasure to be here at Paritech Telecom. So I guess we all know about quantum cryptography here. The really amazing thing about it is it allows us to directly test the secrecy of our communication. And this is because, as we all know, quantum theory tells us that if anyone tries to eavesdrop on the communication, then that unavoidably changes the encoding of the quantum states, and that change in the encoding can be sensed by the system, telling us that it's not secret. So it gives us a way to detect unauthorized eavesdropping on optical fiber, something which is quite unique and can't be done in any other way, and also a way to distribute secret digital keys with a security level that we can quantify. So those are really very useful properties, and several applications have already been either proposed or demonstrated. For example, for link encryption, we can use quantum cryptography along with a symmetric cipher to encrypt the data, for instance, sent in a disaster recovery scenario between a data center and a backup center, or to secure medical records in healthcare networks, or financial transactions in bank networks, or for highly confidential communications on mobile phones, or for securing the fiber optic networks that are increasingly used to control critical infrastructure these days, or in national security applications. Now, to date, most of these implementations have been made on dark fiber infrastructures and using simple point-to-point links or meshes of point-to-point links. But today I'd like to ask the question, can we operate quantum key distribution in a telecom network? So here the challenges are, can we operate QKD with existing network architectures? So in a conventional network, we have complex architectures like metro rings, for example, or we have multi-user access networks. Can we operate QKD in those types of fiber optic system? And secondly, can we send quantum signals along with conventional data along the same fiber? And we believe that this is really a very important issue because the cost of installing a dedicated network for quantum cryptography is really prohibitive for most applications. It's very expensive indeed. So if we want to see widespread adoption of QKD, it's really essential that we can apply QKD directly to the telecom network and not in its own dedicated infrastructure. Okay, so here's the outline of what I'll talk about today. I'll first of all say some things about QKD component technology, and then move on to talk about QKD and networks. First of all, talking about architectures and our work to integrate QKD into access networks. Then I'll talk about the multiplexing of QKD with conventional data and operating QKD on live networks, and finally conclude with an outlook for the future. Okay, so first of all, I'd like to tell you a little bit about QKD technology before moving on to talk about networks. And I'm going to concentrate largely on our own QKD system, which is based on phase encoding of weak coherent pulses. So here's a schematic of the optical layout within that system. The photons are generated by a highly attenuated pulse laser diode. And then the quantum information is encoded in a Mach-Zehnder interferometer, as you see here. And finally detected by single photon detectors at the other end. And I won't go into great detail about the whole system, but I'd just like to highlight a few features of this system, which is relevant to the discussion later on. So first of all, we've developed special single photon detectors, which we call the self-differencing avalanche photodiode. And this is able to detect very weak avalanches and count photons up to very high rates of around 1 billion photons per second, and also detect within a narrow detection window. And this is what allows very high T rates, allows us to use the detector in multi-user networks, and also to operate on live fibers. And another feature of the system is that we use an active stabilization technique And this uses continuous monitoring and adjustment of the photon polarization and phase arriving at the receiver. And that allows a long-term and stable operation. And then finally, we've implemented a variant of the decoy protocol, which we call the T12 protocol. And that allows us to achieve very high security levels and also high key rates as well. So concerning our detector, first of all, that's based on an avalanche photodiode, an InGaAs indium phosphide avalanche photodiode. So a photon creates an electron-hole pair, and then our PIN junction is reverse biased. So that creates an avalanche of carriers, producing a detectable pulse of current from the device. We've developed a device where we can detect very brief and very weak avalanches. And this means that we create much smaller avalanches than is usually the case, and allows us to avoid carrier trapping effects, which can dominate these devices. So normally these very brief and very weak avalanches would be dominated by the capacitive response of the APD to the gating signal, which is applied to the APD. But what we've done is to design a circuit which compares the output from the device with that in the preceding period. And that has the effect of cancelling out this capacitive response of the APD and leaves us with just a very much weaker single photon avalanche signal that you see here. So because our detection circuit is able to detect very weak avalanches, that means that we can now create more of those avalanches every second. And we can now gate the device with gigahertz gating frequencies, and we can detect much higher photon rates in the infrared than has been possible in the past, up to 1 billion photons per second, in fact. And we developed this device a few years ago, and just very recently we've seen, in fact, that the device can also work very well at room temperature. So previously we've cooled the device with thermoelectric cooling to around minus 30 degrees C. Here we tested at room temperature of 20 degrees C. And you can see, increasing the temperature, we get an increase in the dark count rate within the device at a constant detection efficiency. But we also get a decrease in the after pulse rate at the same detection efficiency as well. And this is very easy to understand because when we increase the temperature, then we reduce the carrier trapping effects, which are the cause of the after pulse noise. So the net effect of increasing the dark count rate and decreasing the after pulse rate is that it's still possible to do QKD with room temperature detectors and fibers up to 100 kilometers in length. And in fact, we find that for fibers which are shorter than 35 kilometers, the system actually works better with room temperature detectors because of this decrease in the after pulse rate. And for fibers longer than 35 kilometers, then we have some decrease in the secure bit rate due to the increase in the dark count rate and a reduction in the maximum range of the QKD system from around 120 kilometers or so to here around 100 kilometers. At the other end of the QKD system, we have the photon source, and a number of different photon sources are possible. So, of course, the ideal source for QKD is a single photon source, and there have been a number of experimental demonstrations of single photon QKD in the past. But despite this, single photon sources are not commercially available. So an alternative to that is an attenuated laser, strongly attenuated laser diode. But here the problem is that Eve can gain some information about the key from the multi-photon pulses, which are inevitably produced by an attenuated laser. And the effect of that is that we must very strongly attenuate our laser, especially for longer fiber lengths. And that has the effect of dramatically lowering the secure bit rate that we can have and reducing the maximum range that the QKD system can operate over. So it was shown a few years ago that we can really significantly increase the secure bit rate by modulating the average intensity of the laser pulses. So we modulate the intensity of the laser pulses so as to create three different classes of a laser pulse. called the signal, the decoy, and the vacuum pulses. And this allows us to very accurately estimate the detection rate and the error rate for the 1 photon pulses created by the laser, and that's what we need in order to determine the secure bit rate. So as you can see, this allows us to achieve much higher secure bit rates than is possible with a simple attenuated laser, and approach the sort of bit rates that are possible in the ideal case, in fact. And because our system works with very high repetition rates, then we need only send a very small fraction of these decoy and vacuum pulses in the total stream of pulses. So it doesn't produce a very large reduction in the secure bit rate compared to the case where we only send signal pulses. Now, we not only need a very high photon generation and detection rate, but also we have to turn those detection events into secure key. And that's the job of the key sifting protocol. So we need a QKD protocol that is secure, which has security which is provable, composable, and quantifiable, which is also practical, so uses off-the-shelf components and can be carried out with reasonable computing resources. And finally, that's also efficient. So in other words, it turns those detection events into a secure key with a high bit rate. And we've devised an original protocol that meets all of these 3 criteria, called the T12 protocol. And this uses 3 decoy pulse intensities with optimum intensities and also probabilities. We use 2 encoding bases, which are also selected with optimum probabilities as well. It considers finite sample sizes, largely using the method of Kai and Sukurani. But here we use a linear programming technique to efficiently estimate the parameters which are needed in the decoy pulse method. And very recently we've also updated this protocol to now include general attacks. This will be published soon. And so from that we derive this expression for the secure key rate, which contains this familiar term here, which relates the secure key rate to the yield of the single photon pulses and the error rate for the single photon pulses. And here we have a correction to the secure key rate due to the information loss due to error correction and finite key size effects, as see here. And you'll notice that the expression contains this parameter epsilon, and epsilon is the security parameter, if you like. It expresses our confidence in the security of the key. So when epsilon is small, then there's a very small probability that Eve knows any information about that key. In fact, we can regard epsilon as the probability of key failure. And in all the work that I'll present here today, we take a very conservative value for this probability of key failure of 10 to the minus 10. And this corresponds to the system producing less than 1 bad key every 30,000 years or so. So it's very unlikely that a compromised key will be produced by the system. Okay, and the T12 protocol has really been designed with key generation efficiency in mind, and it uses 3 tricks to maximize the key generation efficiency. First of all, it uses the decoy pulse protocol, as I've just described. Then secondly, we're efficiently selecting the bases. So one of the 2 bases is selected with much higher probability than the other, as you can see here. And this has the effect of almost doubling the secure key rate, in fact. And then finally, it includes the finite key size effect in a very efficient way. In fact, taking a sample size of around 1 minute, we can get to around 85% of the asymptotic limit for the secure key rate. And again, this is possible because the system works with a very high clock rate, and so it creates lots of samples every second. Otherwise, getting to this fraction of the asymptotic limit would take a much longer time. Okay, and this shows typical results with the system implementing that protocol. So it shows some of the highest secure key rates to date. We have a secure rate of 2.2 megabits per second for 35 kilometers, 1.1 at 50 kilometers, 400 kilobits per second at 65 and 116 at 80 kilometers. And we achieved these high secure key rates despite the fact of taking this very conservative value for the security parameter epsilon of 10 to the minus 10. And I'd just like to mention in passing that we've also been doing long-term field trials of the system. And this is in collaboration with Masahide Sasaki and his colleagues at NICT in Japan. So we've been testing the operation over a 45-kilometer fiber between Kogane, where NICT are based, and Otemachi in the center of Tokyo. And if you'd like to hear some more about that, please visit the poster of my colleague Alex Dixon, which will be presented tomorrow afternoon. Okay, so we've been doing that work as part of a project which is building a metropolitan QKD network in the Tokyo area. And this is a collaboration between NICT, ourselves, Mitsubishi, NEC, NTT, and several others as well. And in fact, there are quite a number of ambitious projects in QKD going on around the world. I think tomorrow we'll hear about the Chinese project. So in China, they have plans to build a 2,000-kilometer link from Beijing to Shanghai, and they've already built 50-node QKD networks into Chinese cities as well. In Canberra, there are plans to build a continuous variable QKD network. In US, there are plans to build a 650-kilometer link from Ohio to Washington in the near future. And in the UK, recently the UK government announced a 270 million investment in quantum technologies, which is just about to begin. And that might also include a quantum communication element as well, at least we hope so. So there's really a lot of initiatives going on at the minute. And with all these global investments in quantum communications at the minute, it's going to be very important that all these different networks work together in the future. And for that to happen, it's very important that we develop industrial standards for QKD. And I chair a group at ETSI, European Telecommunication Standards Institute, that are developing the first standards for QKD. And in particular, we're looking at interoperability of systems, because we'd like all of the systems to work together in the future. And that also helps to stimulate a market in this area, a market for QKD applications, and also to create a supply chain for QKD components. And it's also very important for assuring customers of the security of QKD in the future. So if you work in this area and you think you can make a useful contribution to the work of the Industrial Standards Group, please feel free to get in contact with me. Okay, so now I'd like to move on to talk about QKD and different types of network architecture. And one of the things which really led to an aggressive growth of conventional telecom networks was the concept of an access network. So an access network allows multiple users to share the fiber infrastructure, to share a common connection up to the central office switch owned by the telecom company. And given the important role that it's played in conventional communications, I think it's interesting to explore how we could use access networks in the context of a quantum cryptography network. And in that regard, the most economic way in which to implement an access network is to connect multiple quantum transmitters up to a single quantum receiver. This would allow the users to share both the fiber infrastructure, but also the single photon detector as well. The single photon detector is really the most valuable resource within the QKD system. It's the most expensive part of the quantum cryptography system. So it really makes sense that it's placed at the receiver station, and it's shared by the users. So the idea here is that we'll place the expensive components like the detector at the central office, and then we'll use only cheap components like lasers and modulators at the customer site. this could really lead to much cheaper implementation and much larger quantum cryptography networks in the future compared to what we've had in the past. So to test this idea of a quantum access network, here's the experimental system that we built. And in these first experiments, we're using a simple passive optical combiner. And this is a very common telecom component that's used in fiber to the home type networks, for example. And we've tested different passive optical combiners, which have either 8, 16, 32, or 64 ports. And we connect two quantum transmitters, each operating at a clock frequency of 1 over n, where n is the number of ports on our passive optical combiner, and connect that up to 2 ports of the passive optical combiner. And then we connect our quantum receiver to the common end of the network, operating at the full clock rate of 1 gigahertz. And perhaps the difficult part in this setup is that we must now actively stabilize the phase and polarization of each of our transmitters to the receiver. And we do this using an active stabilization technique, as we do for point-to-point QKD, except here it's a little bit more complicated, because normally the active stabilization would be done at the receiver end. Here we have to actively stabilize both transmitters independently. So we detect at the receiver end, but we apply a pre-compensation for any polarization changes or phase shifts within the system at the transmitter end of the system. But despite that, we find that it works very well. And here are some results taken on a 1x8 passive optical combiner, first of all. So you can see that we have stable operation over 24 hours, and with an average quantum bit error rate of 1.5% and key rate of 45 kilobits per second for each user in this 8-way network. And then we also tested the maximum number of users that such a quantum access network can support. By now, we increase the clock frequency of the 2 transmitters to be 1/2 of the total system clock frequency, so to be 500 megahertz. And this simulates a fully occupied quantum access network. So here you see the secure bitrate that we obtained with those conditions for different passive optical networks. And you can see that even for the case where we have 64 users on the network, we still have a finite secure bitrate. So even with today's technology, we think it'll be possible to create a quantum access network which has 64 users connected to a single fiber connection. And we can also increase the secure bitrate per user by now using DWDM combiners. So DWDM combiners have lower insertion loss than simple passive optical combiners, especially when we have a large number of connections on the combiner. So in fact, for a 40-way DWDM combiner, you can buy commercially a combiner which has an insertion loss of less than 5 dB. But here are results taken with an 8-way DWDM combiner. And in this case, the insertion loss is around 1/6 the value that you would have with a simple passive optical combiner. So we can achieve around 6 times the secure bitrate than is possible with the passive optical combiner. So we have a secure key rate now of around 260 to 300 kilobits per second per user. And this is almost enough for 100 gigabytes of key material per user per month. So really quite a significant bit rate, despite the fact that we're sharing it between multiple users. Okay, so now I'd like to move on to talk about combining quantum and data signals onto the same fiber. And in the past, most field trials and implementations have used dedicated fiber for QKD. So typically, to realize a full secure communication system, we would need 3 fibers, 1 for the data, 1 for the quantum signals, and potentially also an extra fiber for the clock signals. And the problem with that is that these extra fibers which are needed to implement the QKD system are not always available in many situations. And even when they are, they can be prohibitively expensive for all but the most high-value applications. So really what we'd prefer to do is to combine all of those signals onto a single fiber using wavelength divisional multiplexing. So in conventional telecoms, we typically use dense wave divisional multiplexing, and that allows us to send many different data channels along a single fiber using different wavelengths of light. Here what we'd like to do is to use just one of those wavelengths for sending quantum signals, so it can act like a security channel on a conventional DWDM communication system. In that case, there's no longer any need to install extra fiber, and applying QKD would have a marginal cost compared to the first scenario. So it can really open up a much wider range of applications for quantum cryptography compared to what's been possible previously. And this is certainly by no means a new topic. In fact, there have been several studies of multiplexing of QKD and conventional data on a single fiber in the past. It was studied as long ago as 1997, in fact, by Paul Townsend and his colleagues. Paul Townsend by himself, actually, when he worked at British Telecom. But you can see from my table here that it's by no means an easy task, because the secure bit rates that have been reported in the past have been very low, and also the data rates have been quite low as well. And furthermore, there have been no reports using the industry standard data rate at the minute of 10 gigabits per second. Today I'll show that using gigahertz QKD we can achieve much higher secure bit rates, several orders of magnitude higher in fact, and we'll also show that it's possible to use the industry standard 10 gigabit per second data transmission standard. And really this result is perhaps not very surprising, because with gigahertz QKD we have a much higher signal rate, and because of that much higher signal rate we can tolerate much higher noise rates, so we can have more classical data on the fiber at the same time. Okay, so what's the problem here? The problem is that the signals carrying the conventional data are typically much stronger than the quantum signals. In fact, each bit of classical data might be carried by 10 to the 6 photons, while the quantum data, of course, is carried by less than 1 photon per pulse. So the problem is that scattered light from our data laser completely overwhelms the quantum signal. And you can see that here from this spectrum of the Raman signal, measured from a single data laser. You can see that the Raman signal coming from the data laser, in fact, is orders of magnitude higher than what we expect for the quantum signal. So to overcome that problem, what we do is we first of all limit the intensity of the data laser as much as possible. We reduce the intensity while at the same time maintaining error-free data transport. Then we also filter the quantum channel as well, arriving at the receiver. We filter it in wavelength using a narrow bandpass filter, and we also filter it in time as well. And that's due to the fact that our detector has this natural ability to resolve in time. It detects in approximately a 100 picosecond window, so we take a 100 picosecond slice of the photons which are arriving at the receiver. And by filtering in those two ways, we can really very strongly reduce the scattered light on the fiber at the quantum wavelength, reduce it by a factor of around 10 to the 3 to 10 to the 5, and this allows QKD on the same fiber as data transmission, as you'll see in a moment. So we first of all did a lab-based feasibility experiment where we're combining QKD with 10 gigabit per second data. And in these experiments, we have 2 data channels applied bidirectionally on the same fiber, each with a bit rate of 10 gigabit per second. And we're combining QKD and the classical data on a DWDM grid using a DWM combiner. So you can see that we've chosen wavelengths on the DWDM grid, which are all around 1550 nanometers here for both the classical data and also the quantum data as well. And this figure here shows the secure key rate for QKD in the presence of those two classical channels as a function of the length of the fiber. So for short fibers, we find, in fact, we can get very high QKD secure bit rates. In fact, the secure bit rate isn't really affected by the presence of the classical data on the fiber at the same time. And this value, in fact, 2.38, is slightly higher than the value I told you earlier for a 35-kilometer fiber without any data on the fiber. That's just because the detector is a little bit more efficient in this case. And with this sort of bit rate, it's sufficient for 7,000 AES keys per second. So we can really very frequently refresh the encryption key that's used for the AES encryption with the system. The classical data does affect, however, the secure bit rate for longer fiber lengths. Then the noise in the fiber becomes more important. And we find that it reduces the maximum range of the system from around 120 kilometers or so when there's no data in the fiber to around 70 kilometers. And all of these results are achieved despite the fact that we take a very conservative key failure probability security parameter of around 10 to the minus 10. And so in that experiment, we used the trick of reducing the power of the data lasers as much as possible. But in fact, we can also operate QKD on fibers using conventional launch powers for the data laser, here of +3 dBm. Here you can see an experiment operated over a 25-kilometer length of fiber, where we have a secure key rate of 445 kilobits per second, despite using a conventional launch power. And the inset here shows the effect on the secure key rate of the launch power. And you can see that around 0 dBm or so, the key rate starts to decrease, but still finite for quite large launch powers and launch powers that are used in standard telecommunication networks. And in fact, the optimal filter bandwidth is defined by the time bandwidth limit. So it's given by the product of our wavelength filter bandwidth and the temporal bandwidth of our detector. That should be as close to the time bandwidth limit as possible of 0.44. And in the experiments that I've just described, in fact, this time bandwidth product is around 1.5. So it's around 3 times the minimum value. We believe, therefore, that further optimization of this system is possible, and it'll be possible to operate QKD over a 50-kilometer length of fiber using conventional launch powers. Okay, so following the successful lab experiments, we thought we'd do a field trial of multiplex QKD and 10 gigabit per second data. And this we did in collaboration with the Telecom operator in the UK, British Telecom, or BT as they're known now, using their fibre network in the east of England, close to Cambridge actually. So we operated a multiplex QKD system between their site in Adastro Park and Ipswich and back again over a 26-kilometer link, which had 10 dB of loss. And also involved in this collaboration were ADVA Optical Networking, and they lent us a system for 10G DWDM data transmission. So this system that you see here can send multiple 10 gigabit per second data channels on an optical fiber, and it's also capable of wire speed data encryption of each of those channels using AES encryption. So here we combine now 4 data channels from the data transmission system, all around a wavelength of 1530 nanometers, along with a QKD channel around 1550 nanometers, and they're combined using a CWDM combiner and then transmitted along the installed fiber and received at the other end. So we're able here we're multiplexing QKD with an aggregate data bandwidth of 40 gigabits per second. And then we use the quantum keys, which are formed by QKD, to now frequently refresh the encryption key that's used for the AES encryption within the data transmission system. So we believe that this is the first implementation of quantum encryption of 10 gigabit per second data, and also an installed fiber as well. And this now shows some of the results from that field trial. So in the first experiment, we launched 4 forward propagating data channels along with the QKD channel. And you can see that we have a QBER of around 6% and a secure data rate of around 160 kilobits per second in this case, with a key failure probability of 10 to the minus 10. And then we also did a second experiment where now we launch 2 data channels in the forward direction, and we have 2 data channels in the backward direction. So we make a bidirectional link on a single fiber for a lower cost implementation. And again, you can see that we have a finite secure key rate with the presence of the 4 10G data channels on the same fiber. Now with a slightly lower QKD key rate of 110 kilobits per second. That's because the QBER is slightly higher in this case because of the backscattered light coming from the backward traveling data channels, in this case coming back to the detector. That creates the backward propagating light creates more Raman noise than the forward propagating signal, because the forward propagating signal is attenuated by the fiber by the time it reaches the receiver. But both cases are certainly possible. And finally, let me say what the outlook is for multiplexing data and QKD in the future. So if we want to multiplex as many data channels on the optical fiber as possible, then what we should do is we should reduce the power of the data channels as much as possible. And 2 ways to do that are, first of all, to use receiver preamplification, to put an amplifier in front of our detector. That allows us to use a lower launch power. And secondly, to use forward error correction, which again allows us to use a lower launch power because we can have a lower received signal. In fact, with forward error correction, we can correct all the errors with a prefec bit error rate of around 10 to the minus 5 or so. So we can use a received power at our receiver of around minus 37 dBm. And here we show a calculation of the secure key rate as a function of the number of channels launched on the same fiber, each with a launch power of minus 26 dBm. And because our channel has a loss of 10 dBm, that means the power at the receiver in this case would be minus 36 dBm. So it should give us error-free data transport with that launch power. And you can see that even for the case that we have 128 data channels on the same fiber as the QKD link, we have a finite secure key rate. So we believe it'll be possible to achieve much higher multiplex bandwidths in the future, even up to a terabit per second accumulated bandwidth. Oh, and I should also mention that we simulated this case as well by now increasing. So here we're also using 4 data channels, but now we increase the laser power so as to simulate the effect of having more data channels on the system. And you can see that our experimental data agrees very well with this simulation. And this is, of course, for an unoptimized system. If we optimize the temporal and the wavelength filtering, then it may be possible to achieve even higher data bandwidths on the same fiber as QKD. Okay, so finally then let me summarize by saying point-to-point QKD is now getting very highly advanced. We have megabit per second secure key rates, quantified security, and we can use room temperature devices. Also, long-term operation has been proven in network environments. There are concepts for large-scale, low-cost networks, for example, using quantum access networks. And we've demonstrated that up to 64 users are possible on such a quantum access network. So really can vastly expand the scale of networks we've seen so far. And integration with telecom networks is really essential for achieving widespread adoption of the technology. We've seen a megabit per second QKD can be multiplexed with up to 40 gigabit per second data, and this is demonstrated on installed fiber. And we think that there's a prospect of much higher data bandwidths in the future, even up to terabit per second. So finally, let me thank all of my collaborators who've helped me with this work at Toshiba Research Europe, also Toshiba in Japan as well. Please visit the poster of my colleague Alex Dixon tomorrow. He'll tell you about the field trials in Japan. At NICT, at British Telecom, at ADVA Optical Networking, and finally at the National Physical Laboratory. And thank you very much for your attention.
Andrew, very impressive technical development on part of Toshiba. I'm really impressed. But I have a question. At what point in the development do you plan to address practical security? For example, there was a publication last year by a Chinese group where they demonstrated hacking a self-differencing detector of the type that you use. Do you have anything to say about that?
Yeah, we are very interested in implementation security. And in fact, that's exactly what the ETSI group are concentrating on at the minute. I think it's quite natural in the development cycle that we're at the stage now close to implementations, real-world implementations, where we have to think about the implementation security. And certainly that is something that we're working on as well. And like I say, the ETSI group are focusing upon that aspect because we think standards about implementation security will be very important for reassuring customers about the security of QKD.
For the experiment of the QKD with the classical communication, could you tell what's the bandwidth of your wavelength filtering, the spectral bandwidth?
Yes, that's a good question. I didn't mention that. So we did, actually we used two different spectral bandwidths. So in these experiments we have a filter bandwidth of around 100 gigahertz, which is quite typical for DWDM filters. And to achieve this result, I forgot to mention, although it's written on the slide, that we used a filter which has a bandwidth of 25 gigahertz in this case. And like I say, actually, this isn't the optimal value because the optimal value is given by the time bandwidth limit, so maybe somewhat narrower than that.
Yes, you were getting nice results with the passive optical combiner, but if you impose some discipline on these sources so that they would have to wait a few milliseconds or something, you could even use a mechanical multiplexer for the combiner with very little insertion loss. So of course, that doesn't mean everybody can talk at the same time, but have you considered that?
Yes, time divisional multiplexing.
Yeah, time division.
Yeah, that's absolutely another possibility. Yeah. I guess the advantage of wavelength divisional multiplexing is that all the customers can talk at the same time.
You showed the slide which had the different islands of quantum networks or quantum key distribution networks, which are currently under development in different parts of the world. I would like to know or could you say something about your opinion, how those islands could eventually combine, on which kind of level? Like, I mean, they all have their different protocols between the quantum layer, the management layer, and then this actually application layer. Do you think that they will remain independent islands, or would there be a kind of path forward to putting them together?
No, we very much hope that standards will be developed in this area, and then that will allow interoperability of these different systems. So you're quite right that it's really an essential development at the minute that there are standards for common key management layers, for example. And for stimulating the market, that's really very important because when a vendor makes a QKD system, for instance, they want to be able to sell it in different places. Or when someone devises an application to work on QKD, they want it to work with every QKD system. And that's really the role of standards, to create that common platform. So it's an important work, standardization at the moment.
In the last part of your talk, you mentioned the prospects of going with high bit rates by adapting, putting many channels, classical channels, and adapting them. And it's more a general question, but do you believe the trend for the market is to adapt classical channels to QKD or to do the opposite? I mean, do you think there is a room for QKD to influence classical communications?
Yes, I think there is. I guess it depends a large extent to how QKD is implemented within the system. But for instance, if QKD is an integral part of the transmission system, for example, then it's quite reasonable that the QKD system can somehow control the intensity of the classical channels.